Hello, my name is Michael Ortega from the Laboratoire d'Informatique de Grenoble in France, and I will present you the third lesson about 3D interaction. This lesson introduces the basic concepts of 3D interaction on desktop configurations, which means keyboard, mouse, and screen. We'll see the used algorithms for selecting a 3D object as well as for manipulating it in the 3D environment. As we saw in the previous lesson, displaying a 3D content implies to define a viewing frustum. The latter corresponds to a projection function that transforms the 3D data into a 2D image. In this lesson, we will consider the perspective projection as it is the most used projection. Indeed, this projection is considered as realistic because it is close to our eye projection. Interacting with 3D objects involves four canonical tasks proposed by Baumann and his team. First, before any manipulation, you have to select the object. That means acquiring or identifying the object of interest from the whole displayed set. Of course, some textual or selection in a list techniques can be used, but here we will see 3D selection. Moreover, we will consider 3D selection in the classical desktop environment, so using a mouse. Next, once the object is selected, three different tasks can be applied on it. Positioning, which means changing the X, Y, and Z coordinates of the object. Rotating, which means changing the orientation of the object. So the current orientation can be defined in many ways like Euler angles, polar angles, or quaternions. And scaling, which means enlarging or shrinking the object. Sometimes two actions can have a similar visual effect. For example, moving the object along the line of sight of the camera is perceived as an object shrinkage. In that case, changing the viewpoint position will help on disambiguating the perception. Selection is then the first 3D manipulation we'll see in this lesson. In our context, selection consists of visually choosing one object among the other displayed objects. For example, in this figure, I would like to select the yellow sphere surrounded by the black circle with my mouse. All people knows how to use a mouse and knows that clicking anywhere on the screen will select the object under the cursor. But how does that work? The principle is called raycasting, and this technique can be explained by the 5 successive steps of the algorithm. First, the click is captured by the system. The latter gives the cursor coordinates that can be in pixels or normalized between 0 and 1. From these cursor coordinates, the 3D position of the cursor on the near plane of the viewing frustum is calculated. A ray is computed from the camera position through the cursor 3D position. The intersections between the ray and all the objects of the 3D scene are computed. The list of the objects that intersect the ray is sorted in order to know which object is the closer to the camera. This object is then selected. This technique is widely used in the current commercial 3D softwares, but can present some limitations when applied basically. Indeed, the critical step of raycasting is the computation of the intersection between the ray and one object. This could have a high complexity in dense environments with objects with complex shapes. That means a mesh with a lot of faces. In these cases, a task as simple as the selection could take too much time for keeping comfortable interactivity. With very simple objects, as spheres for example, the intersection computation can be fast, as it can be done in 2D. Indeed, the projection of a 3D sphere on the screen plane is a circle. So comparing the distance between the cursor position and the center of the circle with the circle radius directly gives the intersection result. Some simple methods also exist with cubes. Considering this, we can imagine a way to partition the 3D space. This leads to the classical bounding box techniques. So, as intersection of a ray with simple shapes like a sphere or a cube can be optimized and then very fast, an improvement of the selection algorithm performances is to put complex objects in such shapes. The computation of all the intersections starts then with computing intersections with these shapes, called bounding boxes. This quickly decreases the size of the list of the potential objects to select, and then improve the selection performances. This well-known method is used in all the commercial 3D modeling softwares. In HCI, improving the selection of 3D objects in terms of computing performances and/or human skills is still an active field and a great challenge. For example, here is a reference of a recent research that improved the selection of moving objects. In that case, authors use heuristic methods for selecting fast-moving objects in dense environments. Applications could be video games, air traffic control, or hyperlinked video media. In the latter, we could imagine a web user that is watching a basketball game and wants to click on a player for seeing its statistics without stopping the live match. Let's now introduce a definition: the degrees of freedom. Degrees of freedom, usually called DOF, are the number of independent dimensions of the motion of a body, like an input device, a human part, or a robot arm, or the possible movements of a virtual object. An input device, like a mouse, has 2 DOF. Indeed, you can move the mouse in only 2 directions, as it is always laying on a flat surface. Complex input devices from virtual reality systems can have more than 6 DOF. With this definition, we can see now the big issue on manipulating 3D objects with a mouse. Each manipulation of a 3D content, positioning, rotation, or scale, can be done on the 3 axes of the 3D environment. These tasks are then 3 DOF tasks. However, the mouse only has 2 DOF. For solving this issue, the most used solutions are called 3D widgets. They are simple 3D objects dedicated to one or more manipulation tasks, and then can be clicked and dragged around. They are intermediate tools between the cursor and the object of interest, and all the manipulations applied to the widget are applied to the object, linearly or not. For example, here, this widget is for rotation. We clearly see a sphere represented by circles. Clicking and dragging one of these circles rotates the object around the vector orthogonal to the selected circle. In this case, the widget allows translation. Clicking and dragging one of the axes will move the object in one dimension along the corresponding axis. In that special case, clicking on the squares will move the object in 2 dimensions, on the surface defined by the square. In 3D scenes, each complex object has a pivot. A pivot is a 3D point on which the manipulations are applied. It could be the gravity center of the object, but also any part in or out of the object itself. This pivot is also manipulated as an object of the scene according to the specific manipulations the user wants to do on the object itself. In the case of articulated objects, each joint could have its own pivot and its own widget. This allows the user to independently manipulate the different parts of the articulated object. More recently, widgets have been proposed for manipulating the viewpoint of the 3D scene. As the camera has its own position and orientation, it can be considered as any other 3D object of the scene. One of the main advantages of the 3D widgets is that they propose a precise interaction with the possibility of constraining it. For example, with the rotation widget presented previously, selecting a circle constrains the rotation around the axis orthogonal to the circle. However, for rapid and non-precise observations of an object, such a technique could be time-consuming, tedious, and for experts only. In the context of such simple manipulations, some techniques exist and do not display the widget. They are based on a kind of intuitive manipulation. The arcball technique is the most used one. The principle of the arcball is to put the object of interest into an invisible sphere. The displacements of the vector on the sphere make arcs that define the rotation as illustrated in the figure. The arc and the center of the sphere define a plane, and the rotation is applied around the orthogonal vector of this plane. The amount of rotation corresponds to the arc length. This technique is intuitive and allows to non-expert users to easily change the orientation of a 3D object. But this technique has some limitations. So please look at the readings I give with this lesson. They present evolutions of the arc-ball. Manipulating 3D is still a great challenge in the HCI domain. As this lesson is only an overview of the basic principles of manipulating 3D objects on desktop configurations, I encourage the viewers of this video to look for recent researches in this domain. In the next lesson, we'll see the recent algorithms and technologies that allow to manipulate 3D content in a wide range of new environments, from the desktop configuration to big virtual reality caves.